Okay, what I want to do now is discuss Zorn's lemma and the proof and statement of the Hahn-Banach theorem. So first, I want to do some of the preliminary definitions and state Zorn's lemma. This does appear, every now and then when you have to prove something about functional analysis. It appears sometimes, particularly in operator theory and operator algebra. So useful definitions and a useful lemma, really an axiom, Zorn's axiom, really. But anyway, so a few definitions that we all have probably seen somewhere. So a poset, short for partially ordered set, is a pair X, where X is just some arbitrary set, and a order, a partial order. So we call this partial order, and it's basically just behaves like usual, less than or equal to on the real line. So what do I mean by that? Well, this has to satisfy transitivity, which is for any A, B, and C in X. So I'll just write that. A, B, C, and X. A less than or equal to B and B less than or equal to C implies that A is less than or equal to C. 2, we have the flexivity for any A in X. A is less than or equal to itself. And last but not least, we have anti-symmetry for any A and B and X. A less than or equal to B and B less than or equal to C. B less than or equal to A implies B equals A. All right, so, A less than B has the obvious meaning. If A is less than or equal to B, or at least I'll just call it less than or equal to, lack of anything better to call it. So A and B are in some poset. So if A is less than or equal to B and A is not equal to B, well, then we're going to write A is strictly less than B. And again, A and B are in just some arbitrary poset. And usually I'll not write this pair here and just denote the poset by big X. Yeah, so typical examples are pretty trivial. For example, just usual less than or equal to on R, or really any subset of R, like the natural numbers, whatever. Or a more interesting example would be, let's say we have some arbitrary set X. X could literally be anything, any set whatsoever. And let's look at the power set, the collection of all subsets of X. And let's look at this partial order here, where A is quote unquote less than or equal to B if A is a subset of B. A and B are both subsets of X. Okay? You can check very easily that this is a poset, a partially ordered set. More generally, we're going to, for us, typical applications of Zorn's lemma, which I'll state in a moment, is going to be applied to not exactly this example here, but something very similar. Basically, just, it's going to be something where it's a subset of the power set. So it's just some collection of subsets of X, and we still want the partial order of set inclusion. Okay. All right, so two more definitions before I can state Zorn's lemma, and I will apply it to proving every vector space has a basis, or what some people call a Hahn basis. Okay. So, so if I have a poset X, and let's say I have Y as a subset of X, then we say little p is an X is an upper bound if the obvious thing is true. Well, Y is less than or equal to P for all Y and big Y. So, yeah, pretty standard definition. And one more definition. If X is a poset M in X is maximal with respect to big X, if kind of the obvious thing is true, X is less than or equal to M for all X in big X. Okay, so let me state Zorn's lemma, and I kind of want to intuitively tell you what Zorn's lemma really is doing. It's a bit hard to do that, really, but I'll try. There's an interesting blog post by Tim Gowers on basically kind of what intuitively Zorn's lemma means. I'll actually post that on Blackboard, and I'm getting my interpretation from that blog post. But anyway, so Zorn's lemma, and you've probably seen this also in algebra, proving that in a ring, every proper ideal is contained in a maximal ideal. Yeah, so let's say we have a post set that's not empty. So X is a post set. And let's say it satisfies the following condition. So every totally, one second. Right, so, 1 second. So actually I need to make one more definition before I do anything. So let me just get rid of this here. And I need to define the concept of totally ordered. So we say that a post set X is totally ordered, TO for totally ordered, Well, you can compare any two elements in X. So either A is less than or equal to B, or B is less than or equal to A. Okay, so let's assume that we have a poset satisfying the following condition, that every totally ordered Y, the subset of X, has an upper bound in X. Okay. So we're assuming that we have a poset X satisfying this condition. This has to be true for every subset Y of X that's totally ordered. Then the claim is X has a maximal element. Okay, so right. So what's the kind of idea behind Zorn's lemma? Well, the idea is as follows. So, right. So let's pick some totally ordered, and I'm being a little, this is just intuitive here, trying to get the intuitive idea of Zorn's lemma. Let's just pick some possibly infinite, totally ordered set. So let's pick some Y1 that's totally ordered. It could be uncountable. We don't know. Let's just pick this here. Okay. So what we want to do is kind of keep adding stuff to Y1 and building. We want to kind of build larger and larger sets and keep getting upper bounds to those larger and larger sets until we eventually have to get a maximal element. Okay. So right, so Y1 is totally ordered. So by assumption, this has an upper bound in X. Y is totally ordered, so by assumption, Y has an upper bound in X. So let's say, let's say X1 tilde. Let's say this is an upper bound of Y1. All right, so we either have two cases now. If X1 tilde is maximal, we're done. There's nothing to do. We've found a maximal element of X. If not, pick X1 strictly larger than X1 tilde and set Y2 to be Y1, where we add on this element. Okay. So because X1 is an upper bound of Y1, and because X1 tilde is an upper bound of Y1, and because X1 is larger than X1 is larger than X1 tilde, this is going to be totally ordered. You can compare any two elements in Y2. That's basically trivial. X1 is larger than everything in Y1, and you can always compare any two elements in Y1. Okay, so this is totally ordered. So just continue. Let's continue on. Y2 is totally ordered, and I'll just do this one more time. By assumption, we can pick something that's an upper bound for Y2. All right. Yeah, I'll do this one more time. You probably get the point. If x2 is maximal, well, again, we're done. If not, pick x2 strictly larger than x2 tilde. So in particular, x2 is larger than x2 tilde. x2 tilde is an upper bound for y2. So x2 is larger than x1. So yeah, set y3 to be y2 x2. Okay, so what we're doing here is intuitively, we're inductively defining these sets and these elements, big Y and little x. That's what we're intuitively doing. Okay. And right, so all we're doing is we just keep adding on to Y1, basically larger and larger, strictly larger and larger and larger elements. So the idea of Zorn's lemma is that this process works. This process always works. The caveat is you might have to do something similar to this, but much funkier, which is like uncountable induction. You might have to do what's called transfinite induction more properly. And I don't want to get into that because that involves ordinal numbers, but the idea is the idea of Zorn's lemma is exactly this here. This is just usual run-of-the-mill, standard bread and butter, countable induction. I'm just inductively defining these sets y's and the elements x's. This might not always work, but if you're willing to do something much more funkier and kind of do like uncountable induction, again, you should look up transfinite induction on Google if you're curious about this. Well, then this always works. Okay. Okay, right. So understand that without this assumption here, that every totally ordered set, a subset y of x, has an upper bound, well, even this process here, this inductive process here, just miserably fails. In particular, there's no guarantee that you could ever even have an upper bound of y1. And this is important to note because without this condition, well, Zorn's lemma miserably fails. So as examples of failures of Zorn's lemma, well, you don't have to look too far and too deep. Take the natural numbers. The natural numbers are totally ordered. Every subset of the natural numbers are totally ordered. but no infinite subset of the natural numbers has an upper bound. It just doesn't. Okay. Or take another example where Zorn's lemma fails because the hypothesis is not satisfied. It's just a real line with usual ordering. Okay. Again, this is certainly totally ordered, so every subset is totally ordered. But certainly, obviously, there are many subsets of R that do not have upper bounds, even though these subsets of R are totally ordered. In particular, the natural numbers doesn't have an upper bound. Yeah, so Zorn's lemma can miserably fail without this assumption that every subset Y of X that's totally ordered has a upper bound. All right, so for homework, I will give you the problem of proving that every inner product space has a maximal orthonormal set. What I'm going to do is something very similar and prove that every vector space has a maximal linearly independent set. Okay. Right. So yeah, so let's just write a definition here. So B here, usually I'll do script B, is a basis. Really, it's usually called a Hamel basis. V, and here V is just some vector space. There's no norm on it at all. It's just a vector space. If B is maximal, and linearly independent. So just make sure we're all on the same page here. Linear independence in this context means that, and I say that because usually in basic linear algebra, we assume, this is maybe countable, or usually we assume that this is a finite linear independent set, but it has the obvious meaning, really, that if I have any finite linear combination, now understand that infinite linear combinations have no meaning whatsoever. So if I have any finite linear combination of stuff in B, so these are elements in B, these are elements in my field F. So F is going to be, for the purposes of the next few videos, either the real numbers or the complex numbers. Okay. So F equals R or C. I mean, everything I do here, you can do over an arbitrary field, but there's really no point. I mean, maybe if you do number theory, you would do some functional analysis involving arbitrary fields, but it's more specialized. So yeah, so all these are 0. Okay. If I have any finite linear combination of stuff in B equals 0, that implies all the coefficients are going to be 0. Makes it a little neater. Okay, and maximal also has the obvious meaning. Let's say I have B prime or let's say B is right. So sorry. Let's say I have a B prime. I do want to keep it as V. Yeah, let's say B is contained in B prime. And let's assume that this is also linearly independent. Well, then this means that the two have to be equal. There is no strictly larger linearly independent set. Okay. Hence, it makes sense to call B maximal. Sorry about that. Okay, right, if it's been a while since you've seen this kind of linear algebra, I just want to state the following easy to prove proposition. I'll leave it for homework. I don't think I'll collect it, but B is a basis V. And yeah, just if you want to look this up, this is what's often called in algebra a Hamel basis, Hamel. So B is a Hamel basis of V if and only if B is maximal. Well, if and only if the usual linear algebra definition of a basis is true. Sorry, don't want maximal. B is linearly independent and spans and by span, again, I mean finite span. It's all finite linear combinations of stuff in B. N is an N, alpha J are in my field, reals are complex numbers, and xj is in B. So this is the definition here of the span. So we need the span to be equal to V. Okay, right. So B is a basis if and only if B is linearly independent and it spans V. The set of all finite linear combinations of stuff in B is all of V. Really, for our purposes, this definition here is just a lot easier and a lot more useful for our purposes. Even though this is a much more, maybe from the linear algebra perspective, this is a much more useful reformulation of the basis definition. Okay, so, right, so let me prove following theorem. So every vector space V that's not trivial. So we know every vector space contains a zero element. Let's assume it's not trivial. Well, every vector space has a Hamel basis. Okay. All right, and the proof idea is basically you start off with you start off with a non-trivial linearly independent set. You ask the question, is it maximal? If it isn't, pick something that's not in the span and basically form a new linearly independent set. You ask the question, is this maximal? If it is, great. If not, you just add something else to it, not in the span, to form a new strictly larger linearly independent set, and you keep going and going and going. That's the intuitive idea of the proof. Now, that doesn't always work. You can't always inductively define a basis that way. As I said, you sometimes have to do kind of what's called uncountable induction, or really what's really called transfinite induction. And to formalize that, we use Zorn's lemma. Okay. Yeah, so again, just want to write this down. Do this in blue. So if you want to look it up, if you're interested in set theory, I don't really know any faculty who are interested in do set theory, unfortunately, but you can look up transfinite induction. Okay, so anyway, enough of that. What is the proof? Well, the proof is as follows. Let me go get the proof here. So actually, before I do that, I need a little bit of a little lemma. So let me just move this down a bit. And this is a lemma I'll leave for homework. I doubt I will collect it. Actually, let me do this here. Let me just rewrite this very quickly. What's this? Sorry about this little waste of time. So every vector space V, not trivial, as a basis. All right, so the lemma we need is as follows. And it's kind of an obvious lemma, really. So if X is a post set that's totally ordered, no matter what it is, doesn't have to be a vector space. So let's say it's a totally ordered post set. And let's assume that we have this over. Let's assume we just have a finite collection of stuff in X. Okay. Then I claim that I can reorder the LJs in a way that where we have a first element, a second element, a third element, et cetera, in the sense that that first element is less than or equal to the second element, less than or equal to the third element, and so on and so forth. And like I said, it's kind of obvious because it's sort of intuitive from the definition of totally ordered. Any two elements in X are comparable. One is less than or equal to the other. So let me formalize that. Then there exists some bijection from 1 to n to 1 to n. So where the following is true. And I'm calling this L, I'm using the notation L because I'm going to, well, I'll explain why in a moment. Yeah, so as I said, exactly this is true. I can reorder the L's in an ascending way. Okay, this element here, my first element is less than or equal to my second element, is less than or equal to, et cetera, this last element. Okay, yeah, and I'll leave this for homework. It's a pretty easy induction proof. I mean, it's obviously true for, well, even just for two elements, it's obviously pretty trivial because of the fact that it's totally ordered. All right, so anyway, what is the proof of this theorem here? Well, let's just, so the key is always to define a useful partially ordered set, okay? So let's say script L is the collection of all linearly independent subsets of my vector space V. Okay. So this is not empty. Right? That's pretty trivial. For the simple reason that if x is not equal to 0, well, then, pretty trivially, this is linearly independent. So this is certainly in script L. Okay, so there's something in script L. Right? Okay, so yeah, so at least this condition is true. We have a post set that's not empty. Okay. Right, so let's just check. Let's say Y is totally ordered. So I want to check the condition. The condition for Zorn's lemma to hold is true. So let's say Y is totally ordered. Okay. So what's my task in order to use Zorn's lemma? So I should mention, of course, by definition, we're trying to find a maximal linearly independent subset. So this is a good choice to use Zorn's lemma with. We want something in L that's maximal. Okay, we want a maximal linearly independent subset. That's exactly what a basis is. Okay, so what do we need to do? We need to show that Y has an upper bound in L. Okay, so we can certainly get an upper bound pretty trivially. We just have to check that it's in L. What do I mean by that? Well, just take the union of all linearly independent sets in Y. Okay. Yeah, so this is clearly true for any linearly independent set L and Y. Okay, because, well, obviously, we're going over all linearly independent sets in Y, L being one of them. So this is definitely a larger, this is a larger set. So the question is this union linearly independent? Is this an upper bound in script L? So let's prove that. Okay. And if we can prove that, we're done. Now this will be my upper bound for y. Okay, right. So it's enough to show that this here is linearly independent. And this is pretty straightforward thanks to this lemma here. And this is why I use the notation L, because I want to apply it to this proof here. And I chose L because L for linearly independent set. I mean, I'll call it whatever the hell I want, but I think L is as good of any choice. Okay, so right, so let's pick xj, pick a finite subset of this union here. Let's assume we have a finite linear combination of the xj's being 0. All right, so, well, each xj is in the union, so just pick Lj, pick this linearly independent set, Lj, containing xj. Okay, and each Lj is in Y. Y is totally ordered by assumption. So I can invoke this lemma here to get exactly this here. So pick a bijection of 1 to n to 1 to n, where L phi 1 is a subset of L phi 2, subset of, et cetera, et cetera. So of course here subset is, set inclusion is my quote unquote less than or equal to, it's my order. So instead of less than or equal to, I'm using, well, subset. So again, I'll just remind you, it's confusing what phi is. It shouldn't be, but just takes 1 to n. And it is a bijection. It's a little neater. Okay, right, but the point here is as follows, and this is very typical of Zorn's lemma application. Well, this means, so every single xj is in one of the Lj's. By what I'm circling in green, every single one of the Lj's is a subset of this L of phi n. Okay? Everything is a subset of L of phi n. Okay? I don't really care what phi n is. I don't care what integer it is. All I care about is all of these are contained in one of these linearly independent sets. Okay? So remember that this here in particular is linearly independent. Well, what does that mean? That means the xj's have to be 0. Okay, so what does that imply? That implies, because we picked an arbitrary finite subset of this union, and we found that a linear combination of this equaling 0 means they have to be 0. Or really, sorry, maybe more clearly, we picked an arbitrary finite linear combination of stuff in the union, set that to be 0, and we proved that means all the field coefficients, field being reals or complex numbers, are 0. So that implies that this is linearly independent. The union here and that proves it. So in other words, this is in script L. So finally, by Zorn's lemma, a maximal element in script L exists. And again, script L is a set of all linearly independent subsets of V, so a maximal linear independent set exists. Okay, so let's state and prove the Hahn-Banach theorem. Okay, so the Hahn-Banach theorem says the following. So let's say X is a normed vector space over either the reals or the complex numbers. Right, so let's say Y is a proper subspace of X. This over a bit. And let's say we have some bounded linear functional defined on Y. So the claim is there exists a bounded linear functional on X where, well, this bounded linear functional extends my original one. And this is norm preserving. So remember, this asterisk here means a dual space. So it's just the set of the space of all bounded linear functionals from X to either C or the reals. Okay, same thing for the subspace Y here. Okay, yeah, so it's norm preserving. So this norm here is the same thing as this restricted norm from Y to F. Okay. So if this is true, then we say phi is a Hahn-Banach extension of phi 0 on X. Okay, so what I want to do is prove this for Hilbert spaces, just to kind of emphasize how wonderful Hilbert spaces are. And the proof is extremely straightforward, because we know what all bounded linear functionals look like. So the proof, if X is a Hilbert space. Okay, so the only problem is, and this is easy to take care of, let's say we don't know if Y is closed or not. Okay? We need to know if Y is closed or not. We need a closed subspace, rather, to invoke the Riesz representation theorem. Well, that's easy to handle. So let's say M is the closure of Y, so that M is a Hilbert space. So let me first extend phi 0 to M, get a Hahn Banach extension to all of M. And that's easy to do. So just define phi tilde in the dual space of M in the obvious way. And we did this last semester. You just basically, so let me do Y, not that it matters much. We'll just take limits. So it's phi 0 of yn. So remember, phi 0 is my original bounded linear functional on y. So we're just extending it to the closure where y is in the closure. So by definition, y is the limit of stuff in big Y. Okay, you can check that this is a Hahn Banach extension. So in particular, it's just trivially setting yn to be y, you get that phi tilde restricted to y is phi 0, and it's pretty trivial to check that this is norm preserving. So in particular, phi tilde from M to the reals or the complex numbers is phi 0, the norm from Y to the reals or complex numbers. Okay. Okay, so now we have, we have a Hahn Banach extension to M star. Now we kind of trivially extend it to all of the Hilbert space. Okay. So by the Riesz representation theorem, there exists x0 in M where the following is true. My phi tilde of x equals x0. Okay. And just remember, in virtue of this here, we have that, well, let's see what we have. Let's continue on before I do anything. So this immediately gives me my Hahn Banach extension. Well, just define this to be x0. So then this is in the dual space of H. With equal norms. That's just really easy to check. We did it a while ago, but still easy to check. Because they are literally the same bounded linear functional. H. And remember, this is equal to my phi 0 on y. So this is a Hahn Banach, or rather, sorry. This is correct, but maybe make this a little clearer. Remember, that this here was equal to the norm of my original bounded linear functional. Okay, so last but not least, so take phi, restrict it to, well, m, or let's restrict it to y rather. Well, phi literally is phi tilde. I mean, they're literally the same. And phi tilde restricted to y, we saw that's phi 0. Right? So, yeah, we're done. Okay. And again, the point is when you have a Hilbert space, count yourself lucky because Hilbert spaces are wonderful. This is just one of dozens of examples to show you how wonderful Hilbert spaces are. Okay, so yeah, let's now prove the Hahn-Banach theorem. So, so I'm going to follow the book's approach, and what the book does is prove the following lemma. The proof is actually quite a bit, it's a bit long, so I'm not going to really go through it. This is on page 53. If you do want to see a proof of it, it's fairly elementary. And basically, so surprisingly, the hardest part of Hahn-Banach theorem proof is actually proving that if you have a subspace and you just add an element not into the subspace, take the span of the subspace and an element not in a subspace, then you can get a Hahn-Banach extension on that slightly larger space. So that's the following lemma. And really, to prove this, you need to use the fact that we are dealing with a vector space over the reals. Otherwise, the proof just doesn't work, just miserably fails. So we have to assume first that f equals r. So we have to prove Hahn-Banach theorem in the case of real scalars. Okay, so, right, so the lemma is given x, y, and phi 0, as in the statement of the Hahn-Banach theorem, let's say little x is in big X, take away big Y. So Y is a subspace, so that means that little x is not in the span of Y, because the span of Y is Y. Y is a subspace. So let's say Y tilde is the span of Y and X. And if there's any confusion of what this means, this is just the set of all linear combinations of stuff in Y and stuff, well, just beta times X. So alpha, beta are real, and Y is in big Y. Okay, then the claim is there exists an HB, a Hahn-Banach extension of phi tilde on Y tilde. Okay. So I'm not claiming that this is a Hahn-Banach extension on all of X. I'm just claiming that this is at least a Hahn-Banach extension of phi, phi 0. Remember, phi 0 is my original bounded linear functional on y. Okay. So I'm just claiming if I add one element to y, then at the very least I can provide a Hahn-Banach extension to that larger subspace. Yeah, and I guess I'll call this phi tilde. I mean, you don't really have to give it a name. But no harm doing that. Okay, right, and like I said, the proof of the lemma is surprisingly long. It's probably the hardest part of, or maybe the most work of the proof of the Hahn-Banach theorem. All right, so now I can prove the Hahn-Banach theorem again for, I'll outline the case for complex numbers. Okay, and really this is just a very typical Zorn's lemma argument. Okay, so we gotta identify a useful poset, and I'm going to use the book's notation. Why not? Okay, so first, well, without loss of generality, I can assume phi 0 well, I can assume the norm of phi 0 is 1. Why? Well, if not, then phi is, so let's assume, yeah, so if not, then we have two cases. Let's just look at the case phi 0 is 0, then just phi is 0 is a Hahn-Banach extension. If phi 0 is 0, there's really nothing to do. If phi 0 is not 0, then the norm is not 0, so then I can just divide by the norm. So if phi 0 is not equal to 0, so if I can prove it in this case here, then all you do is consider this bounded linear functional phi 0 over the norm of phi 0. Just get a Hahn-Banach extension of this, and that'll give me, multiplying by the norm of phi 0, that'll give me a Hahn-Banach extension of phi 0. Okay. If you're a little uneasy about that, then just fill in the details. But okay, so yeah, without loss of generality, we can assume this has norm 1. So let's identify our poset, a convenient poset. Let's say P is, just using the book's notation, all pairs. So I haven't defined an order yet. I'm just looking at all pairs of vector subspaces y prime of x, and here I want this to be, so maybe I'll just write this out here, make it a little clearer. So it's all pairs where y prime is a subspace of X, and phi prime is a Hahn Banach extension of phi 0 on y prime. Okay, so in particular, this is not empty. It's pretty trivial. Because y phi 0 is certainly in P. I mean, phi 0 is defined on y, so y is a subspace of X. Phi 0 is a Hahn Banach extension theorem of itself on the original space. But anyway, that shows that this is not 0. Okay. This is not empty, rather. P is not empty. Okay, so I'm going to define a partial order in kind of the obvious way. So we're going to say y prime and phi prime are less than or equal to y second prime, phi second prime. Both of these are in P. If, so first of all, both of these are Hahn Banach extensions on y prime and y second prime, respectively. So we want y prime to be a vector subspace of y second prime. And of course, in virtue of being in P, both of these are subspaces of big X, which is crucial. And we want phi second prime to be a extension of phi prime on y prime. Okay. Okay, so yeah, so let's just check that the conditions for Zorn's lemma are true. So let's say script C is something that's totally ordered in P. So let's say it's just a collection of subspaces, pairs of subspaces and Hahn Banach extensions to these subspaces. Let's say this is totally ordered. So do what we've done previously. Just take the union of all these YBs. Okay. So I'm going to make two claims that are for homework. This is pretty easy, and this uses, crucially, the fact that we have, by assumption, that C, script C, is just some totally ordered subset of P. Okay. So I claim that N is a subspace of X. So in particular, N is a vector subspace. Obviously, it's a subset of X. Okay, now let's define phi tilde from N to R in the obvious way. Okay, so just simply define phi tilde of y to be phi beta of y if y is in y beta, big Y beta. So homework is that this is well defined. In particular, it could happen that y is in big Y beta prime, so that we define this as phi of beta prime of y. Well, how do you know that the two are the same? Again, that really crucially depends on the fact that we have a totally ordered subset of P. Otherwise, if it wasn't totally ordered, there's absolutely no reason on earth this is well defined, and it wouldn't be. But we do have a total ordering where we picked this ordering in a very precise and crucial way. Okay. Okay, so right. So now I'm going to make another claim, which is that n phi tilde is an upper bound of C in P, meaning that this is actually in P. Okay. Okay. Right. Remember, that's what we have to do for Zorn's lemma. For given an arbitrary, totally ordered subset of P, we have to prove that that has a upper bound within P. Okay. So let's prove that. Why is this true? Well, right, certainly y beta is pretty obviously a subset of n. For all beta, there's nothing there, and is a union of all these y betas. Okay. So in particular, kind of this part is this part is true. Okay. So maybe to clarify, so let's say, yeah, let's say y beta, phi beta is in C. Okay, so then right, so I want to prove that y beta phi beta is less than or equal to n phi tilde. So right, well, there's nothing. That's exactly it, because n is a union, y beta is a subset of n. And so that proves kind of half of what we need for, y beta phi beta to be less than or equal to n phi tilde. Okay. The other half is just as easy, really. So let's say y is in just definition, really. Okay, so phi tilde of y, by definition, remember, is phi beta of y. So that means phi tilde restricted to y beta will in fact equal phi beta. Okay, so that's the other half that we needed right here. Okay, So we've just proven pretty trivially, but we've proved that right, phi beta is less than or equal to n phi tilde. Okay, so we still need to prove that n phi tilde is actually in P, meaning that we need to prove that phi tilde is in fact, it rather in fact has norm 1. Okay, so let's prove that. I'll also just fill in the details quickly that it's an extension of, it actually is an extension of phi 0 on y. But that just follows from the fact that all these phi betas are, but anyway. So yeah, let's check that actually phi tilde is a Hahn-Banach extension. Okay, so if I have y in n, then for some beta, y is in big Y of beta. So we have phi tilde of y, by definition, is phi beta of y, and that's less than or equal to the norm of phi beta from y beta to reals times, move this up a bit, times the norm of y. Well, that's just, we're assuming that this equals 1, because phi beta is a Hahn-Banach extension. Yeah, phi beta is a Hahn-Banach extension of phi 0 to y beta, so that because phi 0 has norm 1, this has norm 1. Phi 0 on y has norm 1. So this is less than or equal to y, and so that implies that the norm of phi tilde from n to r is less than or equal to 1. And we can prove the converse the other direction kind of trivially by definition. Do that nice and quickly. So this is going to be equal to the following. Sup, definition. So norm y equals 1. Y is in n. Okay. Well, for each beta, obviously, as we mentioned, y beta is a subset of n. So certainly this is going to be bigger or equal to taking the sup over a smaller, possibly smaller set. Well, by definition, what is this? This is, by definition, phi beta of y. And this here is equal to the norm of phi beta, which equals 1. Okay. So that means that phi tilde equals 1. And remember, that's exactly what the norm of phi 0 is. Okay, last but not least, let's say if y is in big Y. So remember, big Y actually is a subspace of really each of these Y betas. Okay, so phi tilde of Y, by definition, is phi beta of Y. Well, phi beta itself is a Hahn-Banach extension of phi 0. And hence, this is going to be equal to phi 0 of Y. So phi tilde restricted to Y is phi 0. And so that means that, in fact, this is in script P. Okay. N is a subspace of X, and phi tilde is a Hahn-Banach extension of phi 0 on N. Okay. Okay. Right. Okay, so just to kind of recap here, right, so remember that we said if we have some y beta, phi beta in script C, so we proved that y beta, phi beta, by the definition of my order here, this is less than or equal to n phi tilde, which is in fact in P. So I'm not going to write anything. But since this is arbitrary, we have that n phi tilde is an upper bound of script C in P. Okay. So this is an upper bound of script C in P. And again, what do I mean by in P? Just it meaning it is an element in P. Sorry about that. Okay, so, right, we can use Zorn's lemma. Any arbitrary, totally ordered subset of P has an upper bound in P. That's all we need to invoke Zorn's lemma. Well, we need P also to be non-empty. We showed that trivially. Basically, Y, phi 0, that pair is in P. Okay, right, so by Zorn's lemma, pick, let's call it x infinity, use the book's notation, kind of, why not, I guess. I'm going to keep this to be phi because this is my Hahn-Banach extension that I want. I'll prove that in a second. So we want this to be maximal in script P. Okay. So I claim that x equals x and infinity. And if that's true, then phi is a Hahn-Banach extension on x. And that's what we need to prove. That's the whole point of the Hahn-Banach theorem, that there exists a Hahn-Banach extension of phi 0 on big X. Okay. So how do we prove the claim? Well, let's assume not. Right, so pick little x in big X, take away big X infinity, and let's get a violation of maximality. Now we're going to use that lemma here that I said is really the toughest part of the proof of the Hahn-Banach theorem, or at least the most work. All right, so let's say phi tilde is a Hahn-Banach extension sorry about that, phi to the span of x infinity and x. Okay, so x infinity is a subspace. So certainly little x is not in the span of x infinity, because the span of x infinity is x infinity. Okay? So this is certainly a proper subset of x infinity. Well, that violates maximality. 1 second. Okay, well, right. So, right. So, yeah. So then, what does this give us? We have x. So I guess I should let me fill in some details here. So because it's a Hahn-Banach extension, we have that phi tilde on, let's give this a name, x prime, I guess. So it's a Hahn-Banach extension to x prime, so it's norm preserving. X infinity. Well, this itself is a Hahn-Banach extension, so this is going to be equal to, well, 1. Not that it really matters much, but okay, so phi tilde is a Hahn-Banach extension of phi to what I just wrote as x x prime. So in particular, we have that phi tilde restricted to x infinity equals phi. And we also have that phi tilde from x prime to r is going to be equal to the norm x infinity to r. Well, this itself is a Hahn-Banach extension of phi 0. So this is going to be equal to this here. Well, this is equal to 1, but it's not really important here. Okay, so the last thing to do is check that, in fact, we have a, that phi here is a Hahn-Banach extension of phi 0. So that's pretty straightforward. Okay, so finally, what does this mean? Well, so phi tilde restricted to y. Well, of course, here y is a subset of x infinity. So in particular, we're on x infinity. This is going to be equal to phi restricted to y. And because phi is a Hahn-Banach extension, this is phi 0. So that means that, well, first of all, this pair here, x prime and phi, is in P. And on the other hand, well, we have that, sorry, I meant phi tilde, x prime phi tilde. On the other hand, we just proved that x infinity phi is strictly smaller than x prime phi tilde, simply because well, x infinity is strictly smaller than x prime, and phi tilde restricted to x infinity is just phi. Okay? Well, this violates maximality. So x has to be x infinity. And so phi is a Hahn-Banach extension of phi 0 on x. Okay, so, right, so let's prove a Hahn-Banach theorem. When f is complex numbers. Okay. And I'm going to outline this. I'll leave some things to be checked for homework. Okay, so let's say we have a phi 0 and the dual space of y, where y is a subspace of, not a proper subspace of x. And here I'm going to use comma c to emphasize that we're dealing with a vector space over the complex numbers. So one thing important to remember is that even if you start off with a vector space over the complex numbers, that unto itself is a vector space. And you can certainly, it's certainly well defined to have a real number times anything in that vector space. And hence, you know, any vector space like this here, you can consider as just a vector space over the reals. Okay. So, right, phi, that means this is bounded linear functional from y to c. So let's say u is the real part of phi. So this is a bounded linear functional on y thought of as a vector space over the reals. And it's pretty trivial to check that, sorry, this is phi 0. U is a real part of phi 0. And you can check pretty trivially that phi 0 of x is going to be u of x minus I u of I x for any x in y. Right. And less trivial is that that this actually is norm preserving. Okay. So first of all, you can check that this is linear. This is, well, yeah. So implicit here is that this is linear. So, right. So this is going to be equal to phi 0, y to c. That's not trivial, but it's not too bad to check. Okay, so we have a bounded linear functional in y as a vector space over R. Let's say u in x thought of as a vector space over R. So remember, x is my original vector space over C, but we're treating it as a vector space over R. Let's say this is a Hahn-Banach extension of u, little u on x. Again, thought of as a vector space over the real numbers. Okay. Well, then, if we define, kind of go backwards, this is u of x minus I u of I x. Let me get rid of this parentheses here. So you can check this is a bounded linear functional on x thought of as a vector space over C. And this satisfies, well, the Hahn-Banach conditions. And you can check that this is norm preserving. And hence a Hahn-Banach extension exists. Okay. Okay, so as I said, the next two videos are going to be on applications of the Hahn-Banach theorem. All right, so this was a bit long. Sorry about that. But remember, you can always do double speed. All right, so long. Take care. Bye-bye.